Hello everyone, I'm Yuhao from Colombia. So today my topic is going to be Tarski fixed points. And the complexity of finding a Tarski fixed point has attracted a lot of attention during the past 5 years. And I personally have been working on this problem for 5 years. So in this talk, I'm going to tell you about the whole journey of this problem and our recent progress and very recent progress on this problem. So this is a joint work with Chen and Mihalis Yannakakis, both from Columbia University. So let me start from the Tarski fixed point theorem and some basic definitions used in this theorem. We will work on lattice. The lattice contains a set of elements. I'm using L to denote the set of elements. So we have a partial order on this set of elements. We call this pair a lattice if for any two elements they have a least upper bound or a greatest lower bound. So for example, we have the Boolean lattice. If you take any two sets, the partial order is defined by inclusion. And if you take any two sets, their intersection is the least upper bound and their union is the greatest lower bound. For example, we could also have this lattice. The elements includes all the integer divisors of 60, and the partial order is defined by divisibility. We could also have this grid lattice. If you take any 2 points, x is at most y, if all coordinates of x is at most y. So these are all lattice. And Tarski's theorem will work on complete lattice. So still we have the partial order, but instead of any two elements, we will require any subset has a least upper bound or greatest lower bound. So for example, this Boolean lattice is a complete lattice. The second lattice is also complete lattice, but the third one is not a complete lattice. For example, if you take the whole set, there's no least upper bound of this set. Clear? And trivially, like if you have a finite lattice, is definitely complete. So we are working on a function from a lattice to itself. So we define it to be monotone if you have any 2 points that are comparable. After you take the fx and fy, they should still be comparable. And actually, this function preserves the order. If you have any 2 points that are incomparable at the beginning, then you don't get any guarantee. So this is the notion of monotone function on the lattice. So the Tarski fixed point theorem in 1955 says every monotone function on the complete lattice has a fixed point. In fact, the set of fixed points is also a complete lattice with respect to the original partial order. And this in particular implies there is a least fixed point and a greatest fixed point. Clear? And Tarski fixed point theorem has extensive applications in a lot of fields, like verification, semantics, game theory, and complexity theory. For example, in the seminal paper by Dana Scott, who was a faculty here, he initiated the field of mathematical semantics of computer languages. And if you look at the paper, he used the monotone function on the complete lattice has a fixed point, actually has a least fixed point to define the semantics of the program. And this has been almost a folklore in the community of programming language. If you open a textbook about formal semantics of program language, you will likely see a chapter talking about Tarski's theorem and how to use the least fixed point guaranteed by Tarski's theorem to define the semantics of a program. Today I'm going to talk about more on game theory side and complexity theory side, so I will ignore the verification later on. So if you are not familiar with the notion of lattice like me, don't worry about it, because we are going to work on this very simple lattice. It's the grid lattice. Yeah.
I didn't understand the connection to the formal semantics of a program. Can you explain that some more?
Sure, yeah. So in a program, you always have recursions. Then how do you define the behavior of the program? So you basically, you can view this program as a iteration, this recursion as an iteration. So you start from a basic and you keep iterating that. And Tarski fixed point theorem tells you there's always a least fixed point where you stop. And you can use this to define the semantics of the program. And in practice, people just use this like simple value iteration. We will see it later to find the semantics of the program.
What is the lattice there for the operational semantics of a program?
I think it's going to be the input of the functions, the recursive functions, and you keep like if you, for example, if you want to compute the like n factorial, you may use a recursive function to call it, right? You want to compute factorial n, you recursively call factorial n minus 1 n times n. So this is the simple function, and if you define it, you could start from the 0 and keep like doing this for the recursive. Yeah.
You should think of the lattice of partial functions ordered by inclusion. You start with the empty partial function, and then each iteration fills in a new value.
Okay, so every point in the lattice is a function.
The lattice is some Boolean lattice. Its elements are partial functions from some domains. So.
No, I have difficulty thinking about it. Why don't you continue?
Yeah. So yeah, I'm going to work on this very simple lattice, the grid lattice. So the elements contains a d-dimensional grid, and the length of the grid is capital N. And we define the partial order as x is at most y if and only if you know for all coordinates of x they are at most y. So for example, this is a two-dimensional grid lattice where if you take a point x, all the points in the green rectangle are the points that are greater than x, and all the points in this rectangle are the points that are smaller than x. You can visualize it also in 3D. And for all other points that are not colored, they are not comparable with x. So this is a grid lattice. I guess the most important part of a fixed point theorem is about its existence. Like why there is always a fixed point. In fact, if you work on this grid lattice, the existence is very simple. I'm going to show you in a minute. So you consider this bottom point. If this bottom point is a fixed point, then we are done. There's a fixed point. Otherwise, if you take this fx, it must map to somewhere inside of this cube. And so note that these 2 points are comparable. Like this point is strictly smaller than this point. And if you take f on both sides, by the monotonicity, it should preserve the order. So this means if you keep applying fx, you will get a monotone path from the bottom point until you reach a fixed point. Because this is a finite domain, you must reach a fixed point at some point. Clear? And symmetrically, you can start from the top point, keep iterating the function f until you find a fixed point. These two fixed points could be different from each other, and in general, you could have other different fixed points. So actually, this proof is simple, but it's also constructive in the sense that it not only gives you existence, but also gives you a algorithm to find the fixed point. So this algorithm, like you just do this very simple path following argument, you will get an algorithm with complexity order of d times n, because like each time one of the coordinates must be increased by 1. So there are in total at most d times n times steps. And it has a bonus point, which is always finds the least or greatest fixed point, depending on you start from the bottom point or the top point. So this is what people use in the field of semantics, but in this talk we are interested in finding an arbitrary fixed point, not necessarily the fixed point or least fixed point, arbitrary fixed point. But the big open question for now is whether there is an algorithm with query complexity poly d log n. So note that this algorithm has exponential dependence on log n, so we want a very efficient algorithm in this context.
What is d and what is n?
D is the dimension of the grid, and n is the length of the grid. Clear? Yeah. So I'm going to tell you about the motivation of like finding a arbitrary Tarski fixed point with very efficient algorithm. Basically, by telling you there are many problems subsumed by this problem. So there's a line of game called simplest best game, Minpyof game, and party game. These are very fundamental games in verification, and these games can be reduced to the Tarski fixed point. And also there's another very important game in game theory called supermodular game, where finding a pure Nash equilibrium is equivalent to finding a Tarski fixed point. So all these results all these problems are subsumed by Tarski, and this result was shown by Aksami, Papadimitru, Rubinstein, and Yannakakis in 2020. So this is a very important paper in the literature, and we will come back to this. There's another type of game called bidding game, which can also be reduced to Tarski. In fact, this bidding game was started even back in 1999. There's a very new problem called arrival, which has been extensively studied during the past 10 years. And this problem also reduced to Tarski fixed point. And all the problems in this picture don't have polynomial time algorithm so far. If you can find an arbitrary Tarski fixed point in poly D log query or time, you can solve all these problems in polynomial time. So let me talk slightly more about the complexity status of these games. So most of these problems are in intersection of NP and co-NP, and in fact, like most of them are in UP intersect co-UP, where UP is defined as the non-deterministic polytime, but with the promise that there's a unique certificate. So this is a picture in the book of Avi Wiggerson, where when he introduced this complexity class NP intersect co-NP. You can see there are 3 problems that are in this class, but don't have polytime algorithm. One is factorization, the other is discrete log. So these 2 problems are more like algebraic problems, and they are actually search problems. Like you have to define very carefully so that you can talk about NP intersect co-NP. But the third one is stochastic game, and this is a long-standing open problem for at least 30 years. I'm going to introduce you this problem, the definition of it. So it's a very natural combinatorial game on the graph. Finally, I want to talk about the time complexity of all these problems. So for all these problems, the best known algorithms are either exponential time or sub-exponential time. And the only breakthrough we have is for parity game, where they can show the parity game can be decided in quasi-polynomial time, and this was already a best paper award in Stock 2017. So if you can solve all these problems in polynomial time, that would be a lot of breakthroughs. Okay, let me talk about the simple stochastic game, the definition of it. So it was introduced by Condon in 1992, where you have it is a 2-player zero-sum game, and it is defined on the graph. So you have the vertices of the graph are partitioned by max node, min node, and random node. So think about initially you have a pebble on the node. If a node is on the max node, then the max player can choose one of its outgoing edges to move the pebble to. If it's on the node controlled by the min player, then the min player can choose the one of its outgoing edges to move the pebble to. If it's on a random node, then no player can control it. It will go to either way with half probability. So this is called random node. And we also have 2 special nodes. One is called 0 sync, the other is called 1 sync. So the objective of the max player is to maximize the probability of getting to the 1 sync, and the min player's objective is to minimize the probability of getting to the 1 sync. So it's a 2-player zero-sum game on the graph. And you can define the decision problem naturally as I gave you this game graph, and I gave you where initially the pebble is. You want to know if both players use optimal strategy, if the max player wins with half probability, and this 1/2 is not very important, you can replace it with an arbitrary number. Clear? So this game sounds complicated, but actually it's not, in the sense that it's only asking for solving a system of max, min, and linear equations. So let's say this is your graph. And so I'm telling the fact that actually the winning probability of the max player is you just want to find a number assignment of these nodes is between 0 and 1, such that this satisfy all these kind of equations, max, min, linear equations. For example, if you look at this random node, this 1/3, this number should satisfy half of this plus this. And if you take an arbitrary max node, this thing should be it should satisfy it equals the max of its 2 successors. So it's just solving a system of max-min and linear equations, which looks very simple. But currently we don't have even a sub-exponential time algorithm for this, where it's a sub-exponential in terms of n, the number of nodes. And so to solve these equations is actually equivalent to finding a fixed point of this kind of function, which is clearly monotone. Why is that? If you keep all coordinates the same but increase one coordinate, of course the function value only increase. This is just because of the the monotonicity of these simple operators. So this is a continuous function, and we want to find a fixed point of this monotone function. Actually, we can discretize it with a very high precision, like 1/2 to the polynomial inverse exponential. So this means we are going to get a monotone function on a grid where the length is exponential and the dimension is polynomial. So that means we need to solve this monotone function with polynomial d and log n time complexity. Clear? So this gives you one concrete example of solving monotone functions and why we need this very high precision. Okay, so I will also tell you the problem of arrival. So this is a relatively new problem, but it's also very simple. And there's no randomness within this problem. So the problem is as follows. I give you a directed graph. Let's say with every node with degree at most 2. If a vertex has 2 odd degree, we will label it one of the edge by a solid and one of the edge by dash. I'm going to explain it later, and we also have 2 things. One is called d, the other is called d bar. So again, we have a pebble on this graph. So you will simulate a deterministic procedure, which is if the pebble is on the node, you will follow the solid edge to move it to the next successor. But when it comes back, you should follow the dashed edge. And if it comes back for the third time, you should follow this one and this one. So you are using this edges iteratively. So let me show you this very simple procedure on this example. So let's say the pebble starts from here, and you follow this edge, you follow this edge, and you follow this edge. And then this is the second time that we visit this node, so we follow this edge, and we follow this edge. And this is also the second time, so we go there. Clear? So this is a deterministic procedure, and the decision question is just to decide whether it's eventually going to D or D bar. Clear? And as I said, this has been extensively studied. So these numbers are actually the number of visits for each node. If you simulate this, as we have seen for this example, and actually if you associate every node with an integer variable, you will get a system of equations like this. So these numbers means each x just means how many times we have visited this node, and roughly speaking, if you know that you visited xp for some times, that means roughly half of them goes to xc and half of them go to xd. But there's a tie-breaking rule where you always want to use this solid edge first. So this means you will have either floor or ceilings on these linear equations. And again, this is a fixed point of a monotone function, and the domain of each variable is an integer between 0 and 2 to the n. So again, that means we have a grid with length exponential and dimension polynomial. That means if we want to solve this problem, we have to have an algorithm with polynomial d log n complexity. Clear? Okay, so I have shown you 2 kind of simple monotone functions that we still don't know, very far from solving it in polynomial time. So the main question is that if we can get better algorithms for finding a Tarski fixed point, and certainly we can do better, but it's only in some sense. So back to 1912, there's an algorithm by Dang, T, and Ye that gives you a log n to the d query algorithm for Tarski, for the Tarski problem. So that means if your dimension is very small, you can solve it fairly efficiently. This algorithm is not very hard. I'm going to show you here. So let's say you have a one-dimensional Tarski instance, which is this line. For sure, you will not start from this point and follow the path. That will take you roughly order of n times. But you will query the middle point. You will try to do a binary search. So if you query this point, and let's say this point goes right, then you can claim that there must be a fixed point in this green area. So you can easily do binary search with log n query complexity. So the trickier case starts from the 2 dimension. Suppose you have this grid. What we are going to do, we are going to fix the middle line of this grid and use your favorite binary search algorithm to find a fixed point on this line. Let's say this is the fixed point and we completely ignore the information on the 2nd dimension. Once you find it, this point either directly goes up or directly goes down. Let's say it goes up, then I claim that there must be a fixed point in this green region. So why is that? Because we get this point, and if you imagine that you follow the path from the point, it has to be a monotone path which ends somewhere here, and that point must be a fixed point. So this shows you existence of a fixed point in this region. So in particular, this means if you spend log n queries on this line, you can shrink the whole search space by half. That means overall you have a log square query algorithm for finding a Tarski fixed point.
What is the dimension in the examples that you mentioned?
The dimension. So this is one. Yeah.
In the application.
Right. It's n. So this algorithm itself, it doesn't give you anything better.
Why is it n again? What is it called? The stochastic gain.
Yeah. Oh, n is the number of vertex, and we associate every node a variable. So overall you have.
It's just the number of variables.
Yes. Yeah. Yeah, and if you digest this algorithm, you can very easily generalize to higher dimension. Like for 3D, you fix the middle line, you find a fixed point, use this algorithm, and you can claim there must be a solution in that area. So overall, you get a log n to the D algorithm. And we come back to this paper by Mihalis and Yannakakis, where they in 2020 showed a lower bound of this algorithm, which is if you take dimension 2, any algorithm must make log square queries to solve it. So this is a matching lower bound, and I have a very simple diagram for this lower bound. So suppose this is your like 2-dimensional Tarski instance. I'm going to show you a hard instance and the construction of a family of hard instance. So the hard instance contains an arbitrary monotone path from the bottom point and the top point. And once you have this monotone path, you pick an arbitrary point as your fixed point, and change all these arrows to go towards this fixed point on the path. And then finally, you change all points that are not on the path, go towards this path. So I'm claiming that on this family of instance, you have to spend log square queries to find a fixed point. Actually, find the fixed point because there's only a unique fixed point. So why is that? The iteration is as follows. If I tell you the whole path here, you still have to spend log queries to find it, right? It's essentially a 1-dimensional binary search problem. And then, because you don't know this path, if you query a point, most likely you will get this kind of noisy arrows. And for each point on the path, around it, you have to spend log queries to find a point on the path. So this overall gives you a log square query lower bound. And if you think about this proof strategy, it actually matches the intuition of the algorithm. What did we do for the algorithm? You spend a log n queries to find a point on the path, and then spend log n points on the path to find the fixed point. So this is basically exactly the same thing on both sides. Any questions? Okay. So in their paper, they had a kind of a very important conjecture of showing actually this binary search algorithm is tied for arbitrary constant d. Like if you work on a 3D or 4D or 10D, it should be like the log n to the d should be the correct answer. And the problem is only to generalize this construction to higher dimensions. And there were multiple groups of people working on this problem, and surprisingly, the conjecture was not true. So there's actually a faster algorithm even you go to 3D. In particular, there's a log n square algorithm. So this is so I'm going to show you the key idea. This is the picture that you would use the binary search algorithm to solve the 3D Tarski instance. The key idea is as follows. So you take the same cube, you take the same middle slice. Instead of finding a point like this, it suffices for you to find a point like this. So that is a point such that 3 coordinates are increasing. Like you don't have to find a fixed point on this middle slice, but as long as you find a point such that 3 coordinates are consistent, you are good. Because you can still use the same path following argument starting from this point to claim there must be a fixed point in that area, so everything is the same. So this is almost trivial to everyone, but the non-trivial part is that once you have this observation, why this could be helpful. So let me dig into this idea. Let's say this is your 3D Tarski instance, and you query this point. I'm copying the middle slice in this orange rectangle. You query this point, you get these 2 information. By monotonicity, that implies all points on this line has to go down, and all points on that line has to go right. So this is inferred by monotonicity of the function. If you just use this information, it's no difference with just solving a fixed point on this 2-dimensional instance. But we actually have the 3rd-dimensional information, which is, let's say this point actually goes up, and that by monotonicity implies that all the green points go up. So I'm copying the same information in this picture. My central claim is that if you are just looking for a point such that 3 coordinates are increasing or 3 coordinates are decreasing, it suffices for you to just search the point in the bottom half region. Why is that? So let me do 2 case analysis. So for example, if you consider the point starting from the monotone path starting from this point, either it stays somewhere inside of the bottom area, then that point must be a solution because the first 2 coordinates are fixed. That means no matter the 3rd dimension is going up or going down, that's a solution, right? Or the path may go inside of this area. That's totally possible, but it cannot across this area because of the monotonicity. Because every point on this path should be increasing. Then the claim is that if you look at the intersecting point of the green area, this must be a solution. Why is that? Because all points on this path for the first 2 dimensions are increasing because you are in the monotone path. But again, you know this all the points for the green area are increasing for the 3rd dimension. So this intersecting point must be a solution. So this in particular gives you if you just use 1 query, you can shrink this search space by half, then overall you can use log n queries to find the desired point, and you can use your overall binary search strategy on the like the 3D instance. Clear? So let me restate it. So this is, let me call this problem Tarski star, where you have a monotone function, the original monotone function from a cube to itself, and we are also given a monotone sine function, this b function from the cube to a sine, like -1, 0, or 1. And the problem now is to find a point such that either fx, like the fx is smaller than x and bx is at most 0, or fx is at least x and bx is at least 0. So think about this monotone function as the function, like the 2-dimensional function on this orange space, but the green information is the monotone sine function. So the problem is to find either like a point like this, and just to restate their lemma, their crucial lemma is that there's a log inquiry algorithm for Tarski star, the two-dimensional Tarski star. So let me explain a little bit more about this thing. Like why this problem is total, like why there's always a solution. Because you have a monotone function. If you think about the Tarski fixed point, that point must be a solution. Like you basically get a point fx equals x, then no matter the sign function, that's your solution. But on the other hand, it's very crucial that you don't search for that solution. You don't search for that fixed point. You search for some kind of solution. Clear? Okay. So of course, the natural question that we want to ask next is, what if I go to 3D Tarski star? Can I do better? And I have a picture here. So suppose this is your 3D Tarski star, like you have a function from this 3D to itself, but also you have the actual sign function. So suppose you carry the center point, you get something like +1, -1, +1, -1. So it's a balanced case. And in particular, this first coordinate is increasing, this third coordinate is increasing, and these two implies that all points on the blue slice are actually going right, and all points on the right slice are actually going up. And you also have this negative solution, negative information, the purple one. And we also have the sign function, like the fourth dimension is the sign function, where that by monotonicity that implies all points in this green cube are like -1. So you can do basically the same argument to say, now we have 4 cubes out of 8, and you can argue that there must be a solution in the area that's not colorful. So why is that? If you think about the monotone part starting from the top point, it cannot go inside of this blue area because all these are increasing, but this is a decreasing monotone path. It cannot go to this area, it cannot go to this area, so it either stays in some uncolored area or it goes to this green area. And once you go to this green area, the intersecting point is a solution. So this is basically the same argument. What's bad about this strategy in 3 dimensions is that the shape kind of looks very weird, and we don't know how to, once I tell you this, what is the second query point, we have no idea. But this is somehow good because at least for the first query, even though we cannot argue there is some structure but we don't know how to argue that. But it at least can delete roughly 1/2 of the points. There are some issues. One is the boundary issue. Like for example, when you delete these cubes, you can't delete the boundary of this green cube because we used the intersecting point as the solution. So this might be a minor point, but there's forget about the boundary. There's actually a bigger issue, which is the intersection. So what's going on here is that we showed if you query the center point, there must be a solution outside of this area. But once you query a bunch of different points, you get different kind of sets which contains a fixed point, but you can't take the intersection in general. For example, if you have two, like these are the two sets, we could know that there's a solution in this area, there's a solution in this area, but if you take the intersection, there's no solution. And I have an even more concrete example. So for example, if we go back to the 2 dimension, you query the middle point, and the claim is that there must be a solution in this area. If you query that point, there must be a solution in that area. You take the intersection, it's empty, right? So this is in general a bigger issue that makes the strategy hard to use. Okay, so people got stuck, and let me just say something about higher dimension. So their original Fermi, Pauli, and Savani, their original algorithm gives you roughly like 2/3D algorithm for higher dimension, which is essentially saying because 3D you can save a log, like for every 3D you can save a log. So this is what you can do. And our relatively old paper says actually you can do better than 2/3, like to roughly 1/2. And the key point is that their argument solves the Tarski problem. But we actually say because you can solve the Tarski star problem, like the two-dimensional Tarski star problem with one log n, you can solve it like log n to the half. And then this plus one means there's an all-term search that we remember. So this improvement is something, but I think the more important conceptual message of this thing is that maybe Tarski star is the more correct notion to work with.
Well, why is it more correct notion?
Yeah, because if you go back to the Tarski problem, you can so to work on higher dimension, actually you can directly work on this inner Tarski star problem to get this kind of decomposition result. So.
But are you saying is it like you said there are many applications for Tarski? Like is this Tarski star independently interesting, meaning that it also has many applications, or is it just a tool for solving the Tarski?
Yeah, it's just a tool for solving the Tarski.
It's just a tool for solving Tarski. It's
yes.
not like the Tarski itself is a more interesting abstract.
Yeah, for sure. Yeah,
okay.
and these two problems are roughly equivalent, like with log factor also. So, but it's just when you think about developing more efficient algorithm for Tarski, maybe you should think about more about Tarski star as the correct problem to solve. Okay, so I'm jumping to another type of question called unique Tarski, and the problem is I'm going to show you the motivation for this. So this is our application picture for the Tarski fixed point, and if you look at all these problems are in UP intersect co-UP. They are in this class for good reason, because they can be reduced to a Tarski instance with a unique fixed point. So remember, in general, we could have multiple different fixed points, and this least fixed point and greatest fixed point, it could be different. But if you have a unique fixed point, the picture is essentially like this two paths must meet in the middle. And because these problems can be reduced to a instance like that, we can use the unique fixed point as the unique certificate to show it in UP intersect co-UP. So this motivates us to just study the unique Tarski, like we have a Tarski instance, but we have a premise that it has a unique solution. Can we do this faster than Tarski itself, or maybe we can solve it in polynomial time, so that it already implies a lot of progress and breakthroughs. So this was an open question by EPRY, and our result is no. So actually, the Tarski and unique Tarski, these two problems have exactly the same query complexity. So here I'm not hiding any constant. They have exactly the same query complexity. We achieve this by, of course, reduction, and we introduce a new type of reduction for this purpose, and we think this framework is interesting on its own. So let me refer to a slightly detailed statement. So to prove these two problems have exactly the same query complexity, we actually showed any algorithm for unique Tarski can solve the Tarski problem within the same query complexity. So, so let me interpret what is an algorithm for unique Tarski. This might not be well defined. So in our model, it is a query algorithm, so it makes adaptive queries on the map, like it queries a point, gets the answer, and queries the next point, and until it finds the fixed point. So this is the soundness. If the underlying map indeed has a unique fixed point, then the algorithm should just find it. Otherwise, the algorithm may just give up. So in particular, because it's a query algorithm, it means whenever the query results are not consistent with any monotone function with a unique fixed point, the algorithm just terminates and ultimately I give up, I don't know anything. So this is the definition for an algorithm for unique Tarski. And our basic idea to show this statement is, of course, simulate any given algorithm to use it to solve Tarski problem. So of course we will have trouble. For example, this is the two-dimensional instance. Maybe the algorithm for unique Tarski first queries that point and it gets this answer, and then maybe it queries this point and it gets this answer. Then we are in trouble, because just by these two queries, you can know for sure there must be two different fixed points on different two corners. And then the algorithm just give up. It says, I don't know anything. Yeah. Clear? So we have a bold fix of this kind of simulation, which is, we simulate the algorithm to carry the first point, we get this thing, and we carry this point, we get this answer. But we don't tell algorithm this thing. We will tell the algorithm something different. So in particular, we are going to tell the algorithm that this problem actually is fixed for the second dimension, but for the first dimension it goes right, which implies there must be a fixed point in this red area. And actually, I'm going to tell the algorithm much more information, like all this information. So if you look at all this information, first they are still monotone, of course, and no points on the green area that's made up by me can be a fixed point. So there's no solution outside of the area, and the true solution area is not infected. So this complicated picture is is from actually a step-by-step construction. So it's not from nowhere. So this is a step-by-step reduction. Like if we have the first query result, we break it to two different pieces of information, and we add this blue arrow where these blue arrows are the information inferred by monotonicity. And these green arrows are the new information that I add. And you add the second piece of information, you add more arrow, and so on and so forth. And finally, for all three arrows, I will follow exactly the same thing. But for the last one, I'm going to change it. So this is a very, very rough illustration of the step-by-step construction. So the key property that we are going to make is given basically any partial information, it should have this kind of a unique fixed point area, and also outside of that, there's no fixed point. So this construction itself is very technical, and I can't explain why I set these arrows like this, not that, but this is the high-level idea. And we also have a barrier, so you could ask, maybe maybe you don't have to use this kind of very complicated on-the-fly kind of reduction or manipulation. Maybe there's an efficient reduction, efficient standard reduction from Tarski to unique Tarski. But our result shows if you have such a reduction, that would imply that the Tarski problem can be solved in polynomial queries, which currently we don't know. And this remains a widely open question. And this proof was inspired by the standard. Not standard, the classic result that for Boolean function, the decision tree complexity is upper bounded by NP times co-NP, and it also has some applications in the TFNP, but I'm going to ignore this for now.
Yeah. So, your reduction is not efficient, right? If there is an efficient standard reduction.
Yeah, so this means if you have not this kind of step-by-step construction, but just some you look at you take the Tarski instance and you directly translate it to a unique Tarski instance without any query, like this kind of thing, you would get by this reduction you can solve the Tarski problem in polynomial queries. So yeah, it's sensitive to how you define what is a standard reduction. There's one notion of.
But you can also define an efficiency metric for your reduction.
Yes.
Does it give is it like the blow up polynomial or?
Right. So here the efficient means the standard reduction, the blow up is only poly d log n. If you have such a efficient reduction, you can.
So what about your reduction? There's also a notion of efficiency.
Right. My reduction actually has no blow up. Like you get zero blow up because.
No, but that's just for the number of queries.
Yes.
What about the running time?
Yeah, very good point. We don't have any guarantee on the running time. So our result only holds if you are interested in query complexity, but not for time complexity. Yeah.
So it can be exponential time.
Yes. So far it's exponential time, and there's a hope to make it polynomial time, but we didn't bother to do that. Until someone can give a polytime algorithm for unique Tarski, we will definitely go to make it efficient. Before that, we are more interested in query complexity. Yeah, but it's a very good point, and it is one of the.
But what about the underlying unique Tarski itself? Is the running time efficient or not?
no,
unique Tarski.
Right. So in that reduction, we are given an arbitrary algorithm. That algorithm is some arbitrary query algorithm that we don't have any assumption on its
But
strength.
the underlying, like, there is a polynomial time. This unique thing you talked about is polynomial time. But you're saying basically the underlying thing is polynomial, but after your reduction, it's no longer poly time.
Right, depends. Like you could have a polynomial query algorithm for unique Tarski, but that algorithm itself is also efficient in terms of time. That's also possible.
But is that known or not?
No, that's not known.
Oh, that is not known.
Right.
So basically, when you say the whole talk is measuring complexity in terms of
Queries.
queries.
Yes. Very good point.
Oh.
Very good catch. Yeah, I'm going to show. Actually, I'm going to show you some point related to this query and time in a few slides. Yeah. Okay, so this is the reduction, a new type of reduction from Tarski to unique Tarski, which presumably you cannot use a standard reduction. So my final technical part, which is going to be short, is about Moore's price. So let me slightly recall the issue of intersection. We all remember this picture. Like if you make two queries, you take the intersection, is going to, the candidate set is going to be empty. But if you take a closer look of this picture, think about the second query point. It's actually somewhere here. And if you were using our reduction, you would never get some kind of result like that. You will get something like already manipulated by our reduction, this green arrow. So in some sense, at a very high level, this our adaptive reduction, although its original purpose is for reduction to Tarski to unique Tarski, it actually allows us to take the intersection in some sense, because we are essentially guaranteeing that the underlying solution is a unique solution. If you have a unique solution, this set has a solution, this set has a solution, you can definitely take the intersection. But this is going to be very adaptive, but this is a high level insight from this picture. And our very recent results shows even for the 4-dimensional Tarski, you can solve it with log square queries. And this is based on the so-called query and delete framework. So the core lemma is again the 3-dimensional Tarski, like this complicated picture can be solved with just log queries. So if you look at this picture, we have mentioned each query you can delete 4 out of 8 cubes. And because we don't know any underlying structure, or we can't argue any underlying structure of this picture, especially after a few queries, so we are going to use a counting argument to say, if you give me an arbitrary subset of points as the candidate points, I can show you there must exist a next point after a query in which we can delete a constant fraction of the candidate points. So this, in particular, gives you a log and query algorithm. And this argument itself doesn't rely on the structure of the candidate points just because we don't know how to argue that. And this algorithm itself is query efficient but not time efficient. Because we can only say there is some nice points that you should query and it should make a nice progress, but we don't know how to, it's a counting argument, we don't know how to efficiently find that point. So this algorithm itself is a query efficient algorithm, but it's not time efficient. Does this answer your question?
I'm just still confused. Does your result, like reduction to unique Tarski, do you end up improving Tarski by doing this reduction, or?
Yeah, we end up improving Tarski by this reduction, but not in unique Tarski.
What is the final theorem for and how does it compare with the previous paper's theorem? Just for Tarski?
Oh yeah, so it gives you a direct improvement on Tarski. Like previously for 3D you can do log n, and our result shows you even for 4D you can do log n. So this result, even for 4-dimension you can do log n queries. And this in particular implies log n is the correct answer for dimension 2, 3. Because we have lower bounds even for 2-dimension.
Do you log into the d to the d over 3 for a big D?
Yeah, exactly. Yeah, you plug in this because our result shows this algorithm for Tarski star, so you can plug in our decomposition framework to get in general log n to the 1 over 3D something. So it also gives you polynomial improvement for higher dimension. But I think what's more important or exciting is this log n square is the correct answer for d equals 2, 3, 4. So this theorem itself is heavily based on a generalization, not the original our adaptive reduction, but it's actually a generalization of that. And there seems to be some fundamental obstacles for FFD Tarski, like we are currently got stuck and we don't know how to, for example, we don't know how to get log square for FFD. Yeah, so this is the progress so far. So I'm going to summary and talk about some open problems. So at the beginning, we have seen this very simple existence proof, which is the simple path volume, and this also gives you a D times N algorithm. And we also saw this binary search algorithm. We saw the lower bound proof. We saw the very nice surprising result for D3, the fast algorithm, and that's based on this kind of very nice idea. And then we have seen this a new framework for Tarski to unit Tarski reduction, and we have briefly seen this very recent progress. Even for D4, you get log square queries, and we have also seen some applications for the arrival problem. And
in this D equal to 3 case, like which part makes the running time not polynomial?
Oh, that's polynomial. That
one has polynomial running time.
Yeah.
But
So
yours is not polynomial.
No, mine is not.
I see.
And that algorithm, because if you remember the picture, so this picture, you can always maintain the candidate set as a very good shape. Like you carry the point, you cut it by half, you carry the point, you cut it by half. So you know the underlying structure is always a rectangle, so you can carry the center. So there's no issue of time complexity. But for our algorithm, after a few queries, we have no idea of the candidate set, so we use a counting argument. Okay. By the way, you could say this is like weakness of our algorithm, but we actually think it's advantage in some sense, because if you insist on time efficient algorithm, it will be very, very hard to work on this shape. So I think once you give up on time complexity, first starting the query complexity, you can actually get the tight answer. And these are the literatures. Yeah, so the time complexity state of the art is our this 1/2 algorithm, which is based on decomposition of the Tarski star, and the query complexity sort as this 1/3 algorithm. And this algorithm itself doesn't run in polynomial or like some efficient notion of. And I think this is the most important message. So I'm going to talk about some open questions. Obviously, the open question is to close the gap of the large gap between upper bound and query bound for query complexity. This is trivial to everyone. I'm going to talk about some other things, some more broad open questions. So one is the more applications of Tarski fixed point. So we all know this arrival problem. It now has a sub-exponential time algorithm which explicitly exploits the Tarski fixed point. Like inside of their sub-exponential time algorithms, they actually use the Tarski's fixed point with the binary search. But what's more important is they don't associate each variable, each node a variable. They actually pick a root number of important nodes to work on kind of a smaller dimension of Tarski problem, and you use a binary search algorithm for that. That gives you roughly a 2 to the root n time algorithm. So this is a very nice idea. And in terms of lower bound, we could ask, if we don't work on the gray lattice, but any lattice, maybe we just want to show arbitrary lattice that you need log cube queries to find a fixed point, or log to the 2.1 or something. And also we have seen the adaptive reduction that helps the Tarski problem itself, but we could ask if there's more applications of the adaptive reduction, this new framework. And that's all of my talks. Thank you.